I put some examples in here, and there's also more examples in the textbook in the reading, and I highly recommend you look at these because really you're going to learn by looking at specific examples. And so, for example, you guys have seen IR spectra already. You've seen what they look like, but you know, we see these peaks right here on the left. These look really big, and the reason for it, again, is because really normally they would be kind of medium or even weak, but there's no really strong peaks in this, so it blew them up to full scale. Does that make sense? But at any rate, see these peaks here? These peaks are what CH stretches look like. There's usually more than one. They all come together in a group, okay? Technically, they're sharp, but because they overlap, they just look like a blob with points on the top, okay? We also have, in this example, CH bending peaks, which there's usually two. It's like 1450 and 1375 or 1360. They're weaker. They're sharp, but they're a lot weaker. Sometimes you don't see them. Sometimes there's a lot of garbage on them, okay? If we look, you can see here's a C double bond C stretch. This here is the CH for the sp2 hybridized carbon, and then there's sp3 hybridized carbon CHs. You can see that when you go to an sp2 hybridized carbon hydrogen, the bond is a little shorter, it's a little stronger, vibrates a little higher frequency, okay? And then we get other kinds of peaks like this, okay? This is probably a harmonic overtone of this really big peak. This is out of plane bending of the CHs, of the double bond. So the double bond is flat, okay? It's flat, and then the hydrogens vibrate up and down like this, out of the plane, okay? And you can see that's a really strong vibration. And then it turns out, if we look at the frequency, that frequency is just a little bit above 900. Do you see that? What is that? Probably about 915. Okay, everybody cool with that? So it turns out that these vibrations, they work like the vibrations of a string. And I don't know if you're familiar with the vibrations of a string. Like you take a string and you pluck it and it vibrates. It has one main vibration, and then it has what are called harmonics, where in whole number ratios, the string vibrates. Like if you take the string, one is the whole string vibrating, then the second one is half the string vibrating this way, half the string vibrating this way. That's at twice the frequency, and then there's one at 3 and so forth, okay? Those are called harmonics. The main thing about harmonics is that they are approximately whole number multiples of the original vibration. So if you look, here's 915, look at here, do you see this? That's 2 times 915, it's a harmonic. I hope that makes sense, but. So that second vibration is caused by the first vibration. Do you see? We see these very often if there's low frequency, really strong vibrations. Do you see? Here's another harmonic. That's the 2 times 1000. Because look, see here, here's the 1000. Does that make sense? So that's why the IRs start to look really complicated. But what we're going to do is focus on the ones that we can understand, okay? All right. I want to show you, this is an OH. Most OHs of alcohols, I'm going to just make that distinction. OHs of alcohols, they come right around 3,300 or so. It's a little bit above it. Do you see that? Where the highest part is, just a little bit above 3,300. Okay, and they're very broad. You know, so it's really wide peak as opposed to like this peak over here, which is really narrow, right? Broad, narrow, sharp. Amines, nitrogen and oxygen are almost the same weight, okay? And their bond strengths are a little bit different. And so the nitrogens come in almost, NHs come in almost the same place, but with NHs, you get a sharp spike. And usually you get, if it's got one hydrogen, there's one spike. If it's got two hydrogens, there's two spikes, okay? Here's an aldehyde. Do you see, here's the C double bond O of the aldehyde right there. Do you see that? And then look, this is at 1720. So 3400, almost in 40. It's a little bit less. That's the harmonic. Do you see it? 2 times 1700. This is a carboxylic acid. Carboxylic acid has an OH. But the OH of a carboxylic acid comes at a lower frequency. Do you see? It's centered about 2900. But do you see it's this whole thing? It's super broad. Okay? So do you see how that looks different from the alcohol one? The alcohol one would be more like this. So we can tell the difference by the frequency, the shape, and its location, right? And finally then, this is an amide. If you look, an amide has that NH2. See? NH2, so 2 peaks. Close to where the alcohol is, little bit lower frequency, sharp peaks in it instead of one big broad peak, okay? And then here we have, this is actually the C double bond O, and I'm going to be honest with you, I can't remember why there's 2 of these. I think it might have to do with whether it's hydrogen bonding or not. I'm not even sure. But amides have resonance. It weakens the C double bond O. So because it's weaker, it goes to a lower frequency than your normal C double bond O.